Have you ever pondered why time seems to fly when you're having fun, yet drags when you're bored? This riddle of our existence hinges on the concept of time, a dimension as fundamental as it is enigmatic. Our perception of time is a subjective experience, an internal metronome beating in sync with our own unique rhythms. It's elastic, stretching and compressing based on our emotions, circumstances, and even our age. To a child, a year may feel like an eternity, while adults often marvel at how swiftly the years seem to pass. Yet in contrast to this malleable experience of time, we have the unwavering tick-tock of a clock, each second measured with mathematical precision, seemingly immune to the whims of human perception. But what if I told you that time doesn't always tick away at a constant rate? Let's dive into the world of time dilation. Time dilation might sound like a concept straight out of a science fiction novel, but it's a real phenomenon deeply rooted in the realm of physics. At its core, time dilation is a difference in elapsed time as measured by two observers due to a relative velocity between them or to a difference in gravitational potential between their locations. This mind-bending concept was first predicted by Albert Einstein's theory of relativity. Let's break it down a bit. According to Einstein's special theory of relativity, time for a moving clock or observer slows down as compared to a stationary clock or observer. This is known as time dilation due to relative velocity. You might be thinking, wait, so if I'm moving fast enough, time will slow down for me? Well, in a nutshell, yes. But you'd have to be moving extremely fast, close to the speed of light fast, for the effects to be noticeable. Now, Einstein didn't stop there. His general theory of relativity expanded on this concept to include the influence of gravity on time. Just as speed can affect the flow of time, so too can gravity. This is known as gravitational time dilation. The stronger the gravity, the slower time moves. This means that time ticks faster at higher altitudes, where gravity is weaker, than at lower altitudes, where gravity is stronger. So, if you were to compare two clocks, one at the top of a mountain and one at sea level, the clock at the top of the mountain would run slightly faster than the one at sea level. This might sound absurd, but it's been experimentally verified. These two types of time dilation, one due to speed and the other due to gravity, are fundamental aspects of our universe, and they've been confirmed by numerous experiments. They show us that time isn't a fixed, unchanging entity. So, time isn't as constant as it appears. It's flexible, bending and stretching in response to speed and gravity. To understand time dilation, we need to grasp one of the fundamental postulates of Einstein's theory of relativity. The speed of light is constant for all observers. Now, this might seem like a simple statement, but its implications are mind-boggling. Picture yourself on a train moving at a speed close to that of light. You're holding a flashlight and you turn it on. The light travels from the flashlight to the opposite wall of the train. To you, inside the train, the light has moved a certain distance at the speed of light. Let's bring in another observer standing still outside the train. They also see the light move from your flashlight to the wall, but because the train is moving, they see the light travel a longer path. Here's the kicker. Despite seeing the light travel a longer path, they still see it moving at the same speed, the constant speed of light. This is where time dilation steps in. If speed equals distance over time and the speed of light is always constant, then the time it takes for the light to travel must be different for the two observers. For the observer inside the moving train, time appears to be passing normally. But for the stationary observer outside, time inside the train seems to slow down. Consider a light clock, where time is measured by the bouncing of a light beam between two mirrors. If the light clock is on the moving train, the stationary observer would see the light beam taking a diagonal path, thus covering more distance. But since the speed of light is a constant, it would take more time for the light to bounce back and forth according to the stationary observer. Hence, the clock on the train appears to tick slower. This is time dilation in action. This is the essence of time dilation. The faster you move, the slower time appears to pass for you compared to a stationary observer. This isn't a mere theoretical concept, but a reality that's been confirmed by numerous experiments. So buckle up, we're just getting started with our journey into the labyrinth of time dilation. Gravity is another factor that can bend and stretch time, a concept that might seem even more bizarre. Yes, you heard that right. According to the general theory of relativity, proposed by none other than Albert Einstein, gravity can cause time to slow down. This phenomenon is what we call gravitational time dilation. Let's use an example to illustrate this. Imagine two clocks, one at sea level and another at the top of a mountain. You might think they tick at the same rate, right? Well, not according to Einstein's theory. The clock at sea level, being closer to the gravitational source, the Earth, should tick slower than the clock at the top of the mountain. This is because gravity is stronger at sea level than it is at the top of the mountain. Now, why does this happen? To put it simply, gravity is the curvature of space-time caused by mass. The larger the mass, the greater the gravity, and the more space-time curves. And since time is part of that space-time fabric, it gets affected by this curvature too. When gravity increases, time slows down. This might sound like a plot from a sci-fi movie, but it's actually a scientifically proven fact. In fact, the Global Positioning System, or GPS, must account for this time dilation effect. The satellites in space are farther from the Earth's gravitational pull, so their onboard atomic clocks tick faster than identical ones on Earth. If this wasn't accounted for, the GPS system, which relies on precise timing, would quickly become inaccurate. But what if gravity was extremely strong, like near a black hole? In such a scenario, time would stretch so much that it would almost seem to stop. A second near a black hole could feel like hours or even days to an observer far away from the gravitational pull. So if gravity is strong enough, time can stretch, making seconds seem like hours, minutes like days. It's a mind-bending concept, isn't it? But that's the fascinating world of time dilation for you. It challenges our perceptions and makes us question the very nature of reality. While time dilation may seem like a far-fetched concept, it actually affects our everyday life. Let's delve into some intriguing real-world applications and evidence of this phenomenon. You've probably used a global positioning system, or GPS, right? It's a network of satellites that provides location and time information virtually anywhere on Earth. But did you know that these satellites have to correct for time dilation due to their speed and altitude? You see, these satellites are moving at tremendous speeds and are far away from the Earth's surface, which means they experience less gravitational pull. According to Einstein's theory of relativity, both these factors, high speed and weaker gravity, cause time to tick slower for the satellites compared to time on Earth. If these differences weren't accounted for, the GPS coordinates would be off by about 7 miles a day. So every time you use your GPS to find your way, it's actually the theory of time dilation at work, ensuring you reach your destination accurately. Let's look at another fascinating instance: the experiments with atomic clocks on airplanes. These ultra-precise clocks can measure time to billionths of a second. In one such experiment, 2 atomic clocks were synchronized. One was kept on the ground, and the other was flown around the world on a commercial airliner. When the flying clock returned, it was slightly behind the one on the ground. This was a direct demonstration of time dilation. The clock in motion, due to its speed, had experienced a slower passage of time. Time dilation might be a mind-bending concept, but it's not just theoretical. It's a practical, observable phenomenon with real-world implications, from the accuracy of your GPS to the precision of atomic clocks. So next time you check your GPS, remember, it's only accurate because of the mind-bending theory of time dilation. In the grand scheme of the universe, time is not as straightforward as it seems. We've journeyed through the enigma of time, exploring the fascinating concept of time dilation. We've seen how relativity and the speed of light play a significant role in this phenomenon. Faster you move, slower the time appears to you. And it's not just speed, but also gravity that has a say in the ticking of time. The stronger the gravitational pull, the slower time runs. We've also peered into the real-world implications of time dilation. From GPS satellites accounting for this phenomenon to keep us on the right path, to the slight aging difference between astronauts and those of us on Earth, time dilation is not just a theoretical concept, it's a part of our everyday life. So, the next time you feel time slipping away, remember, it might not be just in your head. In the realm of physics, time really can stretch and shrink. Please remember to like and subscribe. For more thought-provoking content, please drop a comment in the box and let know what you would like to see next. Thanks for watching.